Yeah, maybe I should have started. I didn't really. I did it for 3. I did for like 2 and 1.
3 I did.
But 3 I didn't.
I mean, there's not much to show.
Yeah. I think it's just, I think you just have your, I think you have like your axes and stuff. You want to make sure that this one is the velocity and this one's time.
But this is the yeah. Yeah, I think it looks like
Oh, I didn't create a position versus timer.
Oh, we've got one more right waiting. Okay, we'll go ahead and get started here. Share my screen. I haven't been able to fix this. It won't. So I'm just going to continue using it as it is. All right. Okay, can everyone hear me? Okay. All right, hello everyone. I'm going to zoom in. Okay, we're going to review alkanes and naming of alkanes. Then we'll look at cycloalkanes. We'll also look at what are called bicyclic compounds. Okay, as we've said, alkanes are part of a larger family called the hydrocarbons. They consist of only carbon and hydrogens. The maximum hydrogen to carbon ratio that you can have is 2n plus 2 to n. Okay, so any ratio greater than that is not possible. If the ratio is smaller than that, then that would imply either multiple bonds or rings. Okay, because every time you form a ring, you lose 2 hydrogens. Every time you form a double bond, you lose 2 hydrogens. To form a triple bond, then you lose 4 hydrogens. Okay, the alkanes are associated by London dispersion forces, which, as you can see from the boiling points, the London dispersion forces are very weak. So these have really low boiling points. Methane boils at minus 160 Celsius, ethane at minus 89, and propane at minus 42. Propane can be compressed and converted into a liquid, and that can be transported in tanks on trucks or trains. Okay, these are the first 4 alkanes: methane, ethane, butane, methane, ethane, propane, and butane. I'm going to require that you know the names of the first 10 through decane. These are examples of constitutional isomers, where we change the carbon skeleton. These are the isomers of the constitutional isomers of C5H12. A normal pentane or N-pentane is sometimes just called pentane. Okay, and if you hear the name pentane, okay, you're assuming that it means normal pentane, the straight chain. Okay, this is commonly called isopentane, and then this is neopentane. Okay, well, we've started looking at the IUPAC method of nomenclature. Make sure that I'm on screen here. Right, so this is pentane, or sometimes called N-pentane. If we pull one carbon off the end and put it on the second carbon, by the IUPAC, this becomes 2-methyl butane. Okay, a 1-carbon branch is called a methyl. We take methane. Take methane, we remove a hydrogen and attach it to the parent compound, and then this is a methyl. Okay, substituents will end in YL. The parent compound ends in ANE. 2 is the position or locand. Okay, so this is located on position number 2. Right, the other isomer would be this one. Right, this time the longest chain is 3. Okay, no matter which direction you go, it's going to be 3. 3-carbon alkane is propane. And okay, this time we have 2 methyls. Okay, so we use a multiplier prefix. So this is dimethyl. Dimethylpropane. And then every substituent gets a number, even if it's the same substituent on the same position. Okay, so this is 2, 2 dimethylpropane. Okay, each methyl gets its own number. Okay, it would not be correct just to say 2-dimethyl. And you really need the IUPAC system for larger alkanes. Okay, this wasn't too bad. We only have 3 isomers, and we can probably remember the common names. But when we get to 6 carbons, okay, there's 5 isomers. We get to 7, there's 9 isomers. So the number of isomers keeps going up. Okay, well, so let's go ahead and go through the isomers of C6H14. And the first one would be what? 6-carbon alkane is, and this is called hexane. Or you could call it N-hexane for emphasis. Okay, if we remove a carbon off the end, and let's place it on the second carbon here. Okay, this becomes 2-methyl pentane. Okay, because our parent chain is now 5 instead of 6. All right, a third isomer would be this one. And what would it be called?
I can't say.
Oh, I'm sorry. What would this one be called? That's 2-methylpentane.
3-methyl.
3-methylpentane, good. So it's 3-methylpentane. And then, okay, let's shorten the main chain to 4, like this. Okay, so this is a butane. And so we have 2 carbons left over. Okay, so we could put them both on the second one. If we put them back on the first one, that would duplicate. Okay, so we want to stick with our 4-carbon chain. Okay, so this becomes 2, 2, 9-methyl butane.
Dr. Trump?
Yeah.
Khalid said that he hasn't been let in.
Oh, okay, sorry.
Oh, you're good.
All right, let me let him in here.
Thank you.
Okay. All right, so that's 2,2-dimethyl butane. And then the 5th one, butane would be our parent. And what would we call this one?
Which one was it? This one here.
That's 2,2-dimethyl butane. This would be
2,4.
no, close.
2,3.
2,3. Yeah. So this is 2,3-dimethyl butane.
On 2-methylpentane, why do we number it that way instead of numbering it where it would be 4-methylpentane?
according to IUPAC, we want to use the lowest set of numbers. Okay, so if we did this, that's still 2-methylpentane. All I did was just flip it over. Okay, you want to use the lowest numbers. So if I asked you to draw 4-methylpentane, you could do it, but it wouldn't be the correct name.
Okay.
That's what the lowest set of numbers. Okay, so those, the only substituent we worked with there was alcohol. Okay, if we have a branch consisting of 2 carbons, and this is now an ethyl. Okay, so this becomes 3-ethyl pentane. Okay, so would this be 2-ethyl butane? No, it's not. Okay, what's wrong with that name?
But is 4, not 5.
Okay, the longest chain is actually 5, yes. Okay, so we go by the longest chain regardless of how it's written because these chains are flexible. Okay, we can rotate and we can fold and so on. So this would actually be 3-methylpentane. Okay, longest chain is 5. Okay, I think I actually used this as an example last time. 2, 3, 4, 5, 6, 7. Okay, so that's heptane. Heptane is 7. And what's this group called?
Isopropyl.
Isopropyl. Good. That's isopropyl. 4 isopropyl. Okay, notice the difference here between isopropyl and propyl. Okay, propane's 3 carbons. For propyl, we take a hydrogen off the end and attach it to the parent. For isopropyl, we attach it to the middle. Okay, so this would be 4-propyl, or you could also say N-propyl, or propyl heptane. Okay, and this is still the longest chain. Okay, so a 4-carbon branch. Okay, so this is the parent here, and this is a substituent. Okay, so 4-carbon branch would be what? So ethyl, ethyl, propyl. What's the next one?
Butyl.
Butyl. Okay. Must be 4-butyl. Heptane.
But wouldn't you just number it the other way where it's octane?
What's that?
Wouldn't you just number it going up, or wouldn't it be octane that way?
Oh, yeah, you're right. I guess, never mind. Let's make it no names. Yeah, you're right. So let's, we make it nonane. Okay, that would be 5-butyl nonane. If we take the same straight chain, okay, here's our 4-carbon branch. Instead of attaching it to the end carbon of the butane, we'll attach it to the second one. Okay, so this becomes now 5. This would be 5-sec-butyl nonane. Okay, it's a straight carbon chain, but it's connected to the second carbon.
Wait, what was the name again?
4-sec-butyl nonane.
Butyl nonane?
Sec-butyl. Okay. Next, I'm going to review the other 2 butyl groups. These are based on, rather than butane, they're based on isobutane. Okay, so there's 4 of the 4-carbon branches. Okay, we did butyl and sec-butyl. And there's 2 ways of attaching this. We can attach it using the end carbon or the middle carbon. Okay, if we attach it by the end carbon like this, okay, this is now an isobutyl. Okay, so this would be 4 isobutyl, or 5 isobutyl nonane. Okay, so this is like isopropyl, but then you have an extra CH2. Make sure I'm still on screen. Okay, so this is an isobutyl. And then if we keep adding CH2s here, okay, this is now an isopentyl. And if we were to add another CH2, it would be an isohexyl and so on. Okay, and then the last 4-carbon substituent is this one. Okay, and this is called a T-butyl or a tert-butyl. So this is 4-tert-butyl. 4-tert-butyl nonane. Let's go back to the slideshow. Okay, so here's an example of where the longest chain is not the one that's necessarily written horizontally. The longest chain in this case is actually hexane, so this is 3-methylhexane, not 2-ethyl pentane. Okay, here is an example. These are the same structure, but On the one on the right, we have more substituents, so that's considered to be more correct. Okay, and then we alphabetize, we number the longest chain beginning at the end of the chain nearest the substituent. Okay, so this would be 3-ethyl 2,4,5-trimethylheptane. Okay, so here's position 1. Okay, we have a methyl at 2, one at 4, one at 5, and we have an ethyl at 3. We list these alphabetically. Okay, so ethyl comes first. When you're listing alphabetically, the names sec-butyl and T-butyl are actually listed under the B's. If you have a compound that has both a sec-butyl and a tert-butyl, the sec-butyl would come first. Isopropyl and isobutyl are actually under the I's when you're listing these alphabetically. Okay, so here's a summary of some of the different groups: methyl, ethyl, propyl, butyl, pentyl. In the older literature was called amyl. In fact, this is sometimes still used today, amyl, commercially. Okay, these are all the groups that we just went through. Okay, here's another example, 2,2,5,7-trimethylheptane. We use multiplier prefixes if the same substituent occurs more than once. All right, this is what I was talking about with iso groups. Okay, here we have isopropyl, isobutyl. Okay, we've got this isopropyl subunit, and then we've got a CH2 here between the isopropyl and the parent. And then we add another one, another CH2, it becomes isopentyl. And if we add another CH2, it becomes an isohexyl. Okay, so this is 4-isopropyl octane. This is 5-tert-butyl decane. Okay, so we just add this one. Okay, complex substituents. These are substituents of the substituents. Sure that I'm on screen. Okay, so complex substituents. Okay, so that would be 7. Okay, so the parent compound here is 1, 2, 3, 4, 5, 6, 7. So that would be heptane. And okay, what's this on number 3? Group is that? Ethyl. Okay. Okay, so 3-ethyl. And then I'm going to run out of space here. Okay, so on position number 4, we have a complex substituent. We have a substituent with substituents on it. Okay, so this is 1, 2, 3, no matter which way we go. Okay, so we would put that in parentheses. And that would be adjunct here. Okay, so there's a propyl group. And this propyl group has 3 methyls, so it would be 2 trimethylpropyl. In parentheses, and this would be empty. Okay, so all that goes in parentheses.
Do you mind,
Okay, and we number from the point of attachment. Okay, so in this case, when we're naming complex substituents, we don't necessarily worry about the lowest possible numbers. Okay, so the point at which it's attached to the parent, that's number 1 automatically. Okay, so it's 1, 1, 2. Okay, so here is this is not one with a complex substituent, but this is just one with a lot of substituents. Longest chain is 8, so that's octane. We have an isopropyl on 4. We have 4 methyls, so that becomes tetramethyl. 2, 2, 3, 6 tetramethyl. Okay. So whenever we have a tetramethyl, we need 4 numbers. Okay, if I just said 2, 3, 6 tetramethyl, where's the 4th methyl? It doesn't. You don't know. You need 4 numbers. Okay, here's some other examples of complex substituents. Okay, so this is we have an ethyl on 3, and then on position number 5. Okay, so that's where this comes in. Position number 5 on the main chain. And then within the parentheses, we have substituents on the substituent. Okay, so the longest chain, no matter which way you go, is propane, the propyl. And this would be 1 ethyl, 2 methyl propyl. Okay, we list these alphabetically, so ethyl comes before methyl. Okay, we're going to get to cyclic alkanes shortly. Okay, so here is an example of a cyclic alkane. This is cyclooctane. It's take an 8-carbon chain and we join the ends to make a ring. And we use the lowest possible set of numbers off the main ring. So this is 1, 1, 3. 1, 1 dimethyl 3, and then this complex group. Okay, so this is 1, 1, 3 trimethyl butyl. Okay, we got 4 carbons. Start counting from where it's attached, so that's 1, 1, 3. Now this is called cyclooctane. We'll talk about cyclic compounds shortly. Okay, in terms of physical properties, boiling points go up as the number of carbons increases, as the molecular weight increases. Okay, so in blue, we have the normal alkanes. And in green, we have the isoalkanes, where we have a 1 carbon branch at the 2nd carbon. Okay, branching lowers the boiling point. Okay, so we also see a steady increase, but all of these are lower than the corresponding normal alkane. Okay, with melting points also increases the carbon chain increases. But it turns out that alkanes with an even number of carbons have higher melting points than those with an odd number of carbons. Okay, and this is because of the way that the molecules pack in the solid. Turns out that with an even number of carbons, they can pack more efficiently in the solid. And therefore, the blended dispersion forces in the solid are greater, so it takes a higher temperature to melt them. So you can see the zigzag pattern that occurs. Right, alkanes are obtained from natural gas and petroleum. And the primary method to separate the products in crude oil is something we're going to be doing in lab tomorrow, and that's fractional distillation. We'll also be doing simple distillation, and we'll compare the two. But fractional distillation separates compounds based on boiling points. Okay, another important process that goes on in an oil refinery is cracking and hydrocracking. Hydrocracking involves the use of hydrogen gas, heat, and a catalyst. We get a combination of shorter chain alkanes from a larger alkane, and then cracking without the hydrogen gives us an alkene and an alkane. As far as what the catalyst is, that's a proprietary trade secret. But they use a special catalyst for this process. The reason that cracking is used extensively is that not enough gasoline is produced from just distillation. Okay, we get a variety of different products, which we'll see in just a moment here. But it's very economical to take the larger alkanes and break them down into alkanes in the gasoline range. This is actually not a new situation. In fact, actually back around in the late 1920s, fractional distillation did not produce enough gasoline to meet consumer demand. So this is something that's been going on for almost a century. Okay, so this is to produce more gasoline. Okay, so these are some of the various products we can get from distillation. Okay, first of all, the first four alkanes and isobutane are all gases at room temperature. So when you heat up crude oil, these come out of solution and they're collected as gases. You have natural gas, and then also LP gas is propane, stands for liquefied petroleum. Propane is put under pressure, so it's turned into a liquid. Okay, and then we have gasoline. It says on the chart here it's 4 to 9 carbons. This, of course, will vary depending on the season and the temperature. Okay, if you have a hot climate, you would use a larger range. Okay, maybe 6 to 12 or 7 to 12 carbons. In a colder climate, you'd use a smaller range. Okay, and then above gasoline, you have kerosene and jet fuel. Then above that is diesel, then heavy oil, petroleum jelly, paraffin wax, and then the stuff that doesn't distill, is the residue left at the bottom is asphalt. And many refineries will crack asphalt to produce gasoline. And of course, you know, asphalt is used in paving roads. In tomorrow's lab, we're using distillation as a purification technique, but as far as oil refining, I wouldn't call it a purification technique because each one of these sets of products is a mixture of many compounds that have a similar boiling point. Okay, so none of these involve a simple single compound. Okay, so in terms of refining, I wouldn't call it purification. Okay, we're just separating fractions, or we're separating different products based on their boiling point ranges. Okay, here we have some representations of methane. We're changing the subject here. This is the ball and stick model. In the written 3D model, solid lines indicate that those CH bonds are in the plane of the screen. The wedge, with a larger part of the wedge coming out, that indicates that hydrogen is in front of the screen, and then the dash indicates it's back behind the screen. Okay, so here's a ball and stick, and then this is what's called a space filling model. The space filling model more accurately represents the relative size of these atoms. Okay, so we can see that the hydrogen atoms are almost as big as the carbon atom. Okay, they're still smaller, but they're probably bigger than what you would expect. Okay, so this more accurately represents the shape and size of the molecule. Okay, so here's ethane. And we're going to talk about conformations of ethane. And I'm going to zoom in here in just a moment. Okay, in ethane, as the ball and stick model accurately portrays, you can have free rotation about this bond. So let me zoom in here. Working here. Okay. Well, anyway, let's go back to the slideshow. I wanted to show you this with the model, but the zoom is not working here. All right. Well, this is what's called, in the middle, we have what's called a perspective drawing. The wedge hydrogens are in front, the dashed hydrogens are behind. And then if we rotate this 90 degrees so that we're looking along this carbon-carbon bond, Okay, this can be represented by what's called a Newman projection. Okay, in the Newman projection, the carbon in front, we represent this way. We start from the center of the circle, and we have 3 hydrogens. And then the carbon in back, we start those CH bonds from the outside of the circle. Okay, so this is what is called the staggered conformation. Okay, this is where the hydrogens are as far apart as they can get. This CH bond in front bisects this HCH angle in back. Okay, since the carbons are as far apart as they can get, this is the lowest energy, the most stable conformation. Okay, when the hydrogens are lined up like this is called eclipsed. And this is the highest energy conformation. Okay, you have repulsion between the electron cloud on this hydrogen and on this hydrogen. Okay, so these hydrogens are pushing each other away, and that's what's called torsional strain. And the difference between the eclipsed and the staggered is about 12.6 kilojoules per mole. Okay, at room temperature, this rotates freely and that energy barrier is easily overcome. Okay, with propane, we sight along the bond between 1 and 2, and we replace one of the hydrogens with a CH3. Okay, so we have a methyl here in back, like this. This would also be a staggered conformation. And then when all these groups are lined up, that's the eclipsed. Okay, so here's staggered, and then here's another eclipsed. Okay, with butane, we have a couple more conformations. With butane, we sight along the bond between 2 and 3. Okay, so these are the perspective drawings. And these are the Newman projections where we rotate that molecule 90 degrees. So we're looking straight along this 2-3 bond. Okay, we have actually 2 different eclipsed forms. We have one that is totally eclipsed. This is the least stable, where these methyls are lined up exactly. Okay, the other eclipsed is where we have a methyl and a hydrogen lined up. And then if the methyls are 60 degrees apart, this is called gauche. And if the methyls are as far apart as they can get, this is called anti. Anti is the lowest energy, totally eclipsed is the highest. Okay, so this shows the different rotational forms for butane. Anti is the lowest, and then we have these other eclipse forms, and then this is totally eclipsed, the highest energy. And then gauche is a local minimum. Okay, so here we have totally eclipsed, and we have what's called torsional strain here because these methyls are pushing each other apart. And so that introduces a bending strain along this bond called torsional strain. Also called steric hindrance, where these actually bump into each other. Okay, with higher alkanes, all anti-conformations would represent the lowest energy, but you still have free rotation about these bonds. Okay, so next time we will look at cycloalkanes in more detail. So I'm going to go ahead and end here. Tomorrow's lab is simple and fractional distillation.